In the heart of every computer, smartphone, and countless other devices lies a marvel of engineering, the Central Processing Unit or CPU. This tiny chip, often no larger than a thumbnail, is the brain behind your digital experiences. From the simplest tasks like displaying text to complex operations like rendering high-definition graphics, the CPU handles it all. It's the maestro of the digital orchestra, coordinating the actions of every other component in your device. Imagine your computer as a bustling city. Data flows through intricate pathways, programs execute instructions at lightning speed, and the CPU acts as the central command center, ensuring everything runs smoothly and efficiently. Understanding how the CPU works is key to comprehending the power and potential of modern technology. In the following sections, we'll delve into the fascinating world of CPUs, exploring their inner workings and how they've evolved to shape our digital lives. Get ready to explore the beating heart of your digital world. At its core, a CPU's operation boils down to a simple yet elegant three-step process: fetch, decode, and execute. This continuous cycle is the fundamental rhythm of computing, the heartbeat that drives every digital action. The process begins with fetch, where the CPU retrieves instructions from the computer's memory. These instructions, encoded in binary code, a series of zeros and ones, tell the CPU what to do. Next comes decode, where the CPU deciphers the fetched instruction, breaking it down into smaller steps it can understand. Finally, in the execute phase, the CPU carries out the decoded instruction, performing calculations, manipulating data, or controlling other components. Imagine a chef following a recipe. Fetching is like reading the next step in the recipe. Decoding is understanding what ingredients and actions are required, and executing is actually performing those actions. This constant cycle of fetch, decode, and execute repeats billions of times per second, allowing your computer to perform tasks with incredible speed and efficiency. The key to the CPU's incredible power lies in billions of microscopic components called transistors. These tiny electrical switches are the building blocks of modern electronics, acting as gates that control the flow of electricity. In a CPU, transistors are arranged in complex circuits, working together to perform logical operations and calculations. Imagine a light switch. It can be either on or off, representing two states. Similarly, a transistor can either allow current to flow, representing a 1, or block it, representing a 0. By combining billions of these transistors in intricate arrangements, CPUs can perform complex computations and manipulate data at incredible speeds. The more transistors a CPU has, the more powerful it is. This is why we've seen an exponential growth in transistor count over the years, leading to smaller, faster, and more capable processors. From the first microprocessors with a few thousand transistors to today's behemoths with billions, the evolution of transistors has fueled the digital revolution. Another crucial factor influencing CPU performance is clock speed. Measured in gigahertz, clock speed determines how many instructions a CPU can process per second. Think of it as the tempo of the CPU's dance. The higher the clock speed, the faster it can fetch, decode, and execute instructions. Imagine a metronome setting the pace for a musician. The faster the metronome ticks, the faster the musician plays. Similarly, a higher clock speed allows the CPU to process information and complete tasks more quickly. However, just like a musician playing too fast can make mistakes, a CPU running at excessively high clock speeds can generate more heat and become unstable. Balancing clock speed with other factors like the number of cores and the efficiency of the architecture is crucial for achieving optimal CPU performance. While a higher clock speed generally means faster processing, it's not the only factor to consider when evaluating a CPU's capabilities. Section 5. Cores, multiplying processing power. Modern CPUs often feature multiple cores, essentially independent processing units within a single chip. Each core can handle its own set of instructions, allowing the CPU to execute multiple tasks simultaneously. This parallel processing capability is crucial for multitasking and demanding applications. Imagine a team of workers collaborating on a project. Each worker focuses on a specific task, and together they complete the project much faster than a single worker could. Similarly, multiple cores in a CPU can divide and conquer complex tasks, significantly improving performance in multi-threaded applications and games. The number of cores in a CPU can vary widely, from dual-core processors in budget devices to high-end CPUs with dozens of cores. As software becomes increasingly multi-threaded, CPUs with more cores are better equipped to handle the demands of modern computing. Section 6. From kilobytes to terabytes, the evolution of memory. While the CPU is the brain of the computer, it relies heavily on memory to store and retrieve data. Memory acts as a temporary workspace, holding instructions, data, and intermediate results that the CPU needs to access quickly. Over the years, memory technology has advanced alongside CPUs, enabling faster data access and larger storage capacities. Early computers relied on kilobytes of memory, barely enough to store a few pages of text. Today we have terabytes of storage at our disposal, enough to hold massive libraries of multimedia content. This exponential growth in memory capacity has been crucial for supporting the increasing complexity of software and the demands of modern applications. From slow and bulky magnetic tapes to lightning-fast solid-state drives, memory technology has come a long way. The evolution of memory has been instrumental in shaping the capabilities of modern computers and enabling the data-intensive applications we rely on today. Section 7, Instructions per cycle, squeezing out more performance. In addition to clock speed and core count, CPU performance is also influenced by the number of instructions it can execute per clock cycle. This metric, known as instructions per cycle, or IPC, reflects the efficiency of the CPU's architecture and its ability to optimize instruction execution. Imagine a factory worker who can perform multiple tasks simultaneously. A more efficient worker can complete more tasks in the same amount of time, increasing overall productivity. Similarly, a CPU with a higher IPC can execute more instructions per clock cycle, leading to faster processing speeds. CPU designers employ various techniques to improve IPC, such as pipelining, which breaks down instruction execution into smaller stages, and out-of-order execution, which allows the CPU to execute instructions in a different order than they were received, maximizing efficiency. These architectural advancements contribute to the continuous improvement in CPU performance. Section 8. The rise of multi-core processors, parallel processing power. The advent of multi-core processors marked a significant shift in CPU design, enabling parallel processing and unlocking new levels of performance. Instead of relying on a single core to handle all tasks, multi-core CPUs divide and conquer, assigning different cores to execute instructions concurrently. Imagine a team of musicians playing different instruments simultaneously. Each musician contributes to the overall melody, creating a richer and more complex sound. Similarly, multiple cores in a CPU work together to process information and complete tasks more efficiently, especially in applications designed to leverage parallel processing. From dual-core processors in early smartphones to server-grade CPUs with hundreds of cores, multi-core technology has revolutionized computing. As software becomes increasingly multi-threaded, multi-core processors are essential for handling the demands of modern applications and delivering seamless user experiences. Section 9. From Intel 4004 to today's powerhouses, a legacy of innovation. The journey of CPU development is a testament to human ingenuity, characterized by relentless innovation and a constant pursuit of greater processing power. From the humble beginnings of Intel's 4004, the first commercially available microprocessor, to today's sophisticated multi-core behemoths, CPUs have come a long way. Released in 1971, the Intel 4004 packed a mere 2,300 transistors and operated at a clock speed of 740 kHz. Today's CPUs boast billions of transistors and clock speeds exceeding 5 GHz, a testament to the exponential growth in processing power over the past few decades. This remarkable progress is a result of continuous advancements in semiconductor manufacturing, architectural innovations, and the relentless pursuit of miniaturization. From the first microprocessors etched onto silicon wafers to today's nanometer-scale transistors, the evolution of CPU technology is a testament to human ingenuity and the transformative power of technological progress. Section 10. The future of processors, smaller, faster, more efficient. The quest for more powerful CPUs continues, driven by the insatiable demand for faster computing, more immersive experiences, and groundbreaking applications. Researchers and engineers are exploring new frontiers in processor design, pushing the boundaries of performance, efficiency, and miniaturization. One promising avenue is quantum computing, which harnesses the principles of quantum mechanics to perform calculations that are impossible for traditional computers. Quantum computers have the potential to revolutionize fields like medicine, materials science, and artificial intelligence, opening up new realms of possibility. Another area of exploration is neuromorphic computing, which draws inspiration from the human brain to create processors that can learn and adapt like biological neurons. Neuromorphic chips excel at pattern recognition and complex decision-making, paving the way for more intelligent and responsive devices. Section 11 conclusions: CPUs, the unsung heroes of the digital age. CPUs, the tiny brains powering our digital lives, are often overlooked but remain essential to our modern world. From the simplest tasks to the most complex calculations, CPUs are the unsung heroes of the digital age, working tirelessly behind the scenes to enable the technologies we rely on every day. Understanding how CPUs work provides a deeper appreciation for the complexity and sophistication of modern computing. From the intricate dance of fetch, decode, and execute to the power of transistors, clock speed, and cores, CPUs are marvels of engineering that continue to evolve at an astonishing pace. As we venture further into the digital realm, CPUs will continue to play a pivotal role, driving innovation, shaping our experiences, and unlocking new possibilities. So the next time you open a program, browse the internet, or play a video game, take a moment to appreciate the incredible power of the tiny chip that makes it all possible.